Okay, so we have 5 basic gates, right? And each gate has 2 symbols. So this is a symbol for a what? Yeah. So these are what we call positive logic symbols. And why are they called positive logic? So we have negative logic symbols and we have positive logic symbols. Why are they called positive logic? Yeah, all the inputs are high active, right? Which means they're true when they're what? High. Negative logic means they're true when they're low, right? And of course, the complement for this, or the opposite of this, would be some type of OR, right? And what do? Every place that doesn't have a bubble over here, we add it. And every place that does have a bubble, we leave it off. So this would be called an AND. And what's the name of this gate? What? OR, right? Now the Boolean equation for this gate, we'll call the output X in all this. And then we'll call the inputs A, B, C. So this would be A, and B, and C, right? Over here, this would be X. And we'd say A, or B, or C. Then we put a bar across if the input is low active. And then we put a bar across the whole thing if the output is low active. Right? Everybody okay? And an AND has to have at least 2 inputs, 2 or more, right? And then we'll drop back to 2 inputs. This will be an OR. This will be X equal to A or B. It's going to complement to a negative AND. I'm sorry, yeah, a negative AND. So it'll be X is equal to A and B, bar above each term because the inputs are low active, and then a bar across the whole thing because the output's low active. Then we have a NAND. X is equal to A and B. We put a bar across it because the output's low active, right? Then it's going to complement to a negative NOR. But okay, so far. And then we have a NOR. A or B, active low output. That's going to complement to a negative NAND. Oops. I said it, I drew the wrong thing. Now this is not legal mathematically, but it's legal logically. This is the only gate that we will have where the output would be low active. Or that, I'm sorry, so what we're solving for would be negative. This is called a knot. This is called a negative knot. And what's this guy right here? Yeah, buffer. And a buffer is just a go-between, right? There's no such thing as a negative buffer, but a buffer is just a go-between. But what we do when we go between positive and negative logics, so normally when we draw circuits from left, we draw circuits from left to right, right? And the problem with drawing everything in positive logic is we have to go from the output toward the input to figure out how the circuit works. And this was demonstrated in the last worksheet that we did. So the problem is when we draw diagrams, we go from left to right. Well, this first one, it was given a low, and what did you have to do? You had to trace it from right to left to figure out what would be required over here to get that low over there, right? You understand? Come on. Oh, I lost it. Wouldn't copy it. Sorry. So what we had to do is we had to come up here and try to figure this thing out, right? So we said, okay, I need a low right here. It's not stuck in it. This guy. So it said we need a low right here. So what do we have to do? Well, we said all highs. Well, that high's already there and there and there. And then I had to figure out what in the heck do I need on the input to get a high out of an OR gate, right? So this says what? Yeah, any high, right? Oh, I'm sorry, wrong place. And I wrecked it, but it's not easy to do. So we came over here and we said, okay, that's supposed to be a line right there. It means I need a high right there. And it's an OR gate. So what do we have to do? Well, we know that any high gives me a low. So what did I have to do? Yeah, so I had to say all lows give me a high. Right? You understand? Now, when I came over here, I was okay, because that was a high, and I know this says all highs. And then I come up here, I need a high out of that one. Well, it's drawn as an OR gate. And then I got to figure out I need this. So what we had to do is we had to start on what we needed on the output and trace it back to the input. Well, down here, this is drawn in what I refer to as active logic. And what's nice about active logic is you don't have to figure out what it is because the gate itself tells you what it means. So this one down here says, I need all highs to get, I need all lows to get a low, right? The other one says I need what? All lows to get a high. So here, if it's drawn in active logic, we can trace it from the input where? Toward the output, which is the way we need to do it. So active logic, they switch between positive. So this is a positive logic symbol. Why? Because this is a high active input and is a high active output. So this gate was okay, right? Understand. So what's nice about active logic is that you don't have to figure out what's required on the inputs over on the left because the gates are drawn what? Showing you what they need. And I think I showed y'all a print on the floppy disk controller for that computer, and it's drawn in all positive logic, and we're over here trying to figure out what the heck I need over on the left to get what I needed way over here on the right, right? You understand that? So this is what we prefer. This is what we get sometimes, where the draftsman that draws the thing just draws the positive logic symbols. I think I told you about we got a new inverter over in the Curvemaster in Easley before they shut it down, and the whole thing was drawn with nothing but OR gates. The whole diagram was nothing but OR gates. And we said, I don't know where in the world this thing's gonna do anything, right? You understand? And then so what we had to do is we looked up the part numbers. Luckily, they had the part numbers up on the diagrams and found out they wasn't all OR gates. So we had to redraw the whole thing. So you got to understand, a lot of times these draft people that draw up these diagrams, they don't know the difference between negative and positive logic. So that's why we have all these different symbols. So that's why we have 10 symbols. Because these guys, when they're drawn using negative logic, or if they go between negative and positive logic, then they're drawn showing you what they're looking for, right? That makes sense? And I think I erased everything. So we got 5 basic gates, by the way, and those are on the test that's coming up Wednesday, where all those 5 basic gates are up there. You got to know the name of them, right? You understand that, and you got to know the Boolean equation. There's going to be one where you want to take an equation and turn it into a circuit. Everybody understand product of the sum and sum of the products? What does that mean? Outputting on an and, inputting on ors, right? And of course, when we look at an equation, so believe it or not, every equation going between negative and logic and all this other kind of stuff. And like I said, we did get into sum reduction, but what we're doing is we're looking at what the main divider is within the equation. So this right here would represent what we call a sum of the products. Because if I drew the circuit for this, then I'd say I'd have 3 AND gates, right? And then this would feed into a 3 input OR. And that would be the circuit that represents that equation. This would be what we call a sum of the product. And that's just what they call it. I know we're not dealing with math, but unfortunately, this is what the trade calls it, right? Even though it's not actually sums and products, it's ands and ors. But this is just the term that they came up with. And if I took the same equation, and of course I'm going to divide it up. Oops. E or F3. this would be what we call a product of the sum. So that means we're going to output on AND, right? And we're going to input on ORs. Oops, I got that one. It looks like it's connected together. Okay. So a product of the sum is going to input on ORs and output on AND, right? And the sum of the product is going to input on OR. Sum of the products is going to input on AND and output on ORs. And believe it or not, we can take almost any equation and turn it into one of these two. Listen. Well, we're not really multiplying and we're not really adding. It's just that's the name they picked it up for these circuits. So sum of the products would mean that we're sum, which means we're outputting on an OR and we're inputting on AND, right? Product, so you start off with what you're outputting on, product of the sums, and that's going to be outputting on AND, some type of AND, even if it's a NAND or a negative NAND. I mean, really, that's why we can go between the logic gates, and then we can actually convert these things over. So, like I said, we're not going to really get into that. All we need to do is just be able to identify the equation. Because we have a way we can reduce, so we looked at Boolean algebra because that's what I like. Because it deals with, I don't care how many inputs or outputs you got, you can get it into a Boolean equation. We deal with truth tables a little bit, right? You understand? What's the problem with truth tables? Yeah, it depends on. So we're going to get in some pretty complicated circuits, and well, not extremely complicated. We'll talk about some of them, but these guys might have, if they've got 6 inputs, you know, that would be 64 combinations we would have in a truth table. Right? That makes sense. Or but we got another method that we use to reduce the equation. It's called Karnaugh maps, where you set up a grid and you count in a accounting code called gray code. It's really, and then you put your truth table in there. Then you match up ones, and every time you get a one that matches side by side, it means it can be eliminated. But it runs just like a truth table. So that means if I've got 4 inputs, then I'd have a matrix of 16 rows and 16 columns. If I add one more, I'm going to have what? I'm going to have 30. I'm going to jump up to 32. So Karnaugh maps are nice to teach, but they're very ineffective as far as trying to figure out how a circuit works. Where if I've got some type of equation where I say X is equal to A or B, okay, and I come up here and do that, and I said C and D, then I can come up here and I can say, okay, what would the output would be? What would the output be if I've got the equation? Then I don't need a truth table, and I would say, okay, what would the output be if A is a 1 in, so let's say we come up here and we say well, let's make up something. Let's say A is equal to a 1, B is equal to a 0, and C is equal to a 1, and D is equal to a 0. So what would the output would be? Well, what I could do is I could just come up here and substitute this in here. I could say X is equal to A. What's A? A 1. What's B? Or 0. Then I'm going to put a bar above that. And then I'm going to say, okay, what's C equal to a 1 and a 0? Right? You understand? Then I'd come up here and I'd say, well, X would be equal to what's 1 or 1? I mean, I'm sorry, 1 or 0. Yeah, so it'd be a 1. Then that tells me to invert it. And this right here would be a 0. So it'd be X is equal to 0 or 0. So what would the output be? The output would be 0. So what I do if I've got a long bar, I just come up here and do the math. Or do the logic, and then it tells me to do what? Invert the answer. And then I came up with that. Well, I didn't even have to have a truth table. I just did what? I just plugged my values into that equation, and it tells me what I would have for whatever input I need. Whether the equation was 32 terms long or whatever, I could just write down all the terms, just plug it into my equation, and it would tell me if I expected a 0 or a 1, right? Y'all see that? It makes sense. And that's what I like about Boolean algebra. You don't need you don't need a truth table. You don't need a Karnaugh map, right? You don't need a truth table to figure out how it works. And then we can reduce it by a lot of the rules that we learned in algebra. Combining terms, moving stuff around, putting like terms together, right? That you learn in algebra. That's what I like about Boolean algebra. There's one instructor that called it Boolean algebra. I don't know where he got the G at. But Boolean is the... So being able to develop if you can develop the equation for a circuit that an engineer has already designed, and like I said, we don't teach much design in this class because we're a community college. We're not an engineering program. If you were in, an engineering program and you got into digital, you would definitely learn a lot about Boolean algebra, and you would definitely learn a lot about these other techniques that we have to reduce equations. All we did was just get a little insight of what the power of it, right? You understand? Being able, what you can do with Boolean equations. It's just like reducing equations in math. Why do you reduce equations? Because it makes them a lot simpler, right? Y'all understand that? The less terms you have in an equation, the simpler it is. But what's nice about Boolean algebra is that when you reduce that equation, not only are you making the circuit simpler, but you're making the circuit smaller. And we're in a place where smallest is the name of the game, right? You understand? Because smallest, how small you can make a circuit has a lot to do with how much profit you make, right? Right? Or you can sell it cheaper than your competitor. So if you can make the same profit but sell it cheaper, then that's the name of the game, right? And that's what Boolean algebra is really neat about Boolean algebra. So the test, I sent y'all a text and let y'all know that the test review was already up on Blackboard. Y'all got any questions or anything that was on there?
O-red. If anything is O-red with itself, it would be
ORed with itself. It's not O-red. Anytime I start off with this, if it's uppercase letters, it's logic. So I've got to say anything ORed, right? Anything ORed with a 1, right? With a 1. So now y'all understand, right? And that's what I said. How can I use this term in logic and use this term in logic? Well, what we do in logic, if I write it in all uppercase letters, it means it's what? It's logic. If I go, so I could type this. That's not logic. That's the word "and," right?
How would you work that equation?
phrase. Like if, like get your, like who said that did, that one right out of X, break C, that break C. Like that bull. Anything.
Well, you'd say, well, anything ORed with a 1, anything. What does anything mean? It could be a 0 or a 1. Well, it don't make any difference because if I've got one input of an OR set to a 1, the output would be a 1. And that's when you look at that chart I said, I gave you all that says this. A or, and this is, this A, I have to put something right there. This is what? Anything. So I come down here and I say this or 0. Anything ORed with a 0 would give us that thing, right? Does that make sense on those equations?
It does now, but last night when I was taking that test, there's so many of them because I was like, what is the old red? Where? I started panicking.
I don't know how else I would have put it. And we've been putting it all. You say, well, this is logic.
I guess I started panicking.
So that's what. Okay, and then I got to say ORed, right? So what I'll put? A little d.
Yeah, already. That's what I thought already. I just started panicking.
So what did y'all think this said? Ended. Anything and with a 1 is anything, right? Anything and with itself is itself, right? Well, the problem is we have this neat little thing called what? Email. And I've told y'all, if y'all got any problems with these emails, say, what in the world is ORED, right?
But then you would have read, you would look at me like, what?
Well, I picked up on it pretty fast. And this is what we do. And this allows us to do this thing. This allows us to combine the English language with logic, right? So what we do with logic is we write all the words in nothing but what? Uppercase letters. Except when we do negative, we'll say, I usually abbreviate it, negative OR. What's that? What's that?
If it a negative or
so an equal sign through a line through it means not equal, right? Is that on it somewhere?
No, that's
oh yeah. So that was exclusive OR is what you're talking about. So an exclusive OR will always have 2 inputs. And what this guy here does is the output shows what we get when they are not equal. So this says I get a high if they're not equal. So what would I get right here? I get a low, good. These are not equal. These are not equal. And then these right here are equal. Okay. That makes sense. So what required to, so when we do the Boolean equations always consider the output, what's required to get the output to go to a high. So this would be the Boolean equation. Oops. Not A and B or A and not B. That would be this is called an exclusive OR, right? Of course, this is an exclusive NOR. So this shows what we have when the inputs are not. So this says I get a low if they're not equal, right? You understand? So this would give us a 1, right? So we get a high if A and B are low, or if A and B are high. So that's the equation for an exclusive NOR. Not A and B, not A and not B. That's the correct way to say it. Not A and not B, or A and B. And that would be the equation for an exclusive OR. We use exclusive ORs and exclusive NORs for a lot of different things, right? They can generate parity, they can check parity, they can do math, they can tell if two guys are equal or not, are the same or not the same, right? They can do a lot of stuff for us. And this is a combinational logic circuit. And what we're going to find out from now on, guys, all our combinational logic circuits are going to be drawn as rectangles. So we use the exclusive OR so often that it has its own unique symbol. Even though it's a combinational logic gate, a lot of people teach it as a basic logic function because it's used so much, even though it is not a basic gate. And we looked at what made up the inputs and we traced it, but we really do not have to know what's inside that thing. Right, you understand? I don't need to know what makes up an AND gate. Now we're going to look at that so we can understand some of the specifications. And when we start looking at the specifications, we're going to look at the inside of these gates and we're going to see the circuit that makes them up. We're not going to, and we'll get a little glimpse into CMOS. But we're not going to be concerned with exactly what's in there. All we need to know is what logic it does, right? You understand? If it don't do what it's supposed to do, then, well, we'll figure out why. But we'll have a good chance at it, right? All we need to know is what these things do. So we don't need to know what the makeup of an OR gate is. We don't need to know what the makeup of an AND gate is. We do know it's made out of transistors, and he said they're going to be field effect transistors, or it's going to be bipolar junction transistors. But we really don't need to know that. But we need to know how they operate, and we are going to look at the inside of the gate. That'll be one of the next lectures we have. We are going to look at the inside of the gate just so we can understand what syncing and sourcing and driving and fan out and all these other kind of specifications that we're going to look at in the data sheets, and it'll help us understand where they came from. Open collector, tri-state, and we'll look at that. So we can have different types of outputs. We're looking at what we call a totem pole output right now. We'll learn what that means. And then we'll look at open collector, and we'll look at three-state, the different types of outputs that these gates can have. And we'll have a little feel of that too. And then, of course, then we'll probably understand why we have buffers. It don't look like we would need a buffer, right? You understand that? Because they do what? They do no logic. But they got to have a function in life, or they wouldn't have them, right? You understand that? We wouldn't have them, and we'll look at that too and find out why do we need buffers. So, any more questions? So y'all know what ORED is, right? And ANDed. So any questions? All right, guys, let's go to lab.